Hello everyone, I'm Liu Pan, the Chief Product Officer at D2S. It's my privilege today to introduce you TrueMask ILT, the industry's first curvilinear ILT that can actually do full chip in one day. I'm very excited about this product because I started doing IoT since 2004, and I introduced the industry's first commercialized IoT in 2005. As we all know, curvilinear IoT gives the best process window, but the mask writing used to be the biggest roadblock. And that was fixed or removed by the new multi-beam mask writer. However, the conventional IoT is not used for all of the critical layers. And when they used, most of them they used in the hotspot fixed mode. The reason is the runtime takes too long. Sometimes it takes weeks, sometimes it even takes months to calculate. And at D2S, we actually solved that problem. That's why I'm so excited to tell you about this story. And we do work with Micron, this is our partner. And today I'm going to show you some wafer print. And also according to Ezekiel, who is the senior director for their litho and OPC, he said our TrueMask ILT gives a much bigger process window compared to conventional IoT and their complex OPC. So let's see. IoT actually started from a curvilinear shape. In 2005, at that time I was a VP product marketing, and I coined this acronym IoT. So that represents inverse lithography technology. IoT basically based on the target wafer you want to print and mathematically calculate the mask solution. Because we are doing this kind of like inversely, that's why we named it IoT, inverse lithography technology. So in 2005, we have 5 papers presented at Bacchus. Then the next year at SPIE, our CTO Dan Abrams and myself, we presented this first technical paper called Fast Inverse Lithography Technology. As you can see, the patterns we presented is actually a curvilinear pattern. So this kind of curvilinear pattern gives the largest process window. Their number of studies has shown this, and here is one of them. It's a joint study by Samsung, Luminescent, and D2S. It shows those curvilinear IoT patterns without any constraints gives the largest process window compared to those Manhattan IoT patterns. But this creates a huge challenge for the mask industry. The first one is for mask writing. Why is that? Because the mask writer, we call variable shaped beam, the mask writer, they basically have to break those curvilinear patterns into those rectangles. And each rectangle is a shot. So you can imagine for curvilinear pattern, it has to break the pattern into many, many small rectangles. And the write time is actually proportional to the shot, number of shots. Therefore, for curvilinear pattern, it will take a really long time to write. So this used to be the number one roadblock. Then the industry realized this problem, and they invented the new mask writer called multi-beam mask writer. For the multi-beam mask writer, it actually have this array of pixels, like 256,000 pixels or beams. They all write at the same time. And they can control each individual beam to turn it on and off so that they can write whatever shape. It doesn't matter curvilinear or straight Manhattan shapes. It's all written in the constant write time, about like 10 to 15 hours. So that problem is fixed. So according to eBeam Initiative survey, IoT has been treated as one of the most critical lithography technologies by all of those leading semiconductor manufacturing companies. It has been used in those critical layers. However, it has not been used for every critical layers. And for most of them, it has been used in the hotspot fixed mode. That means you only use ILT for those small areas to fix the hotspot. So why is that? That's because the conventional ILT takes too long to compute. It takes weeks, sometimes even months, to compute for a full chip solution. So here, I'm going to show you why. Since we have to handle the full chip, but each CPU can only compute the solution for a small area. So first, we have to break the full chip into those small areas we call partition. Then give those small area to each CPU, and CPU will first calculate the ideal solution, then have to clean up with the mask rules. Then because it has to make the mask more friendly to VSB type of writer, it has to do what we call Manhattanization. It's basically change the mask shape, simplify that into some Manhattan shapes. Then once that step is done, since the shapes are changed, so it has to do re-optimization to re-optimize the solution. Then once you have that, you put them together. Because each partition is calculated separately without knowing the other partitions. So when you put them together, the solution at the stitching boundary may not be consistent. So this creates stitching issues. I'm going to show you later. You are going to see a slide. So then to fix those stitching issues, you basically have to take all the regions next to the partition boundary and recalculate the solution. So this will fix some of the stitching issues, but you won't totally fix the problem because you are actually creating new boundaries. And all of those together make the conventional ILT much slower, and it will be order of magnitude slower than just calculating the ideal ILT solution. And at the D2S, we solved that issue. Firstly, this solution is for multi-beam mask writer. So we are basically trying to come up a curvilinear ILT solution instead of try to Manhattanize it. Secondly, I'm going to give you more details in the next slide, but basically we created this gigantic CPU-GPU pair that actually can handle the full chip just like one partition. So we don't have all those stitching issues and how to fix the stitching issues. So altogether, we just have a single step, which basically doing the curvilinear ILT generation with integrated mask rule compliance. So we come up a solution in the curvilinear space, and it actually satisfies the mask rules. So all of those together, we can actually do a full chip in one day. So basically, we first leverage GPU acceleration, because GPU can do this kind of calculations in pixel domain much faster than CPU, and it has the latest GPU has over 5,000 cores, so it can do all of those computations in parallel. That's why it can actually do it much faster, and also it can actually handle much bigger partition size. Then on top of that, as you can imagine, if we can create a virtual gigantic CPU-GPU pair, we make that bigger, and eventually we can actually handle an area like a full chip. That's exactly what we did. So the result is we have a virtual CPU-GPU pair that actually can process the entire chip at once. So therefore, we don't have any stitching issues at all. So here, let me show you the stitching issue I mentioned in the previous slide. So on this page, you see examples that created by this conventional ILT. So as I mentioned, you have those partitions. So the left partition was calculated separately from the right partition, although they have some buffers in the middle. But still, at the end, you see, look at the solutions that generated from the left. You see this seed feature. Then, unfortunately, the solution you generated from the right partition, you don't see that seed feature cross this boundary. Therefore, you only have a half seed feature at this region, which is not correct. Another common issue is those main features that split it at the partition boundary. Then you see the left solution and the right solution, they are slightly different, right? It creates those jogs. And all of those issues we call partition errors, and they have to be fixed. Well, in our solution, because we have this gigantic CPU-GPU pair that can process the full chip at once, so we don't really have the stitching boundaries, right? So you look at the solution at those boundary, you see the solutions, they are continuous, right? All of those seed features cross that boundary line, they actually continuous. Although, all right, so in the next, let me show you some real mask and wafer result. So this is done together with our partner Micron. So the mask, those multi-beam, is actually written by UFLAR's multi-beam mask writer, MBM 1000. Then the wafer is printed at Micron's fab. So the first, I am going to show you a number of slides. You are going to see the curvilinear ILT mask pattern. Those are some images on the left, and then the corresponding wafer image on the right. So those are wafer images are actually printed using the curvilinear mask that we show on the left. So you see, for each of them, here is basically we'd like to print an array of contact. So you see we actually change the pitch of the contact array, and we also rotate them. And there are a number of things you will notice. First, you look at those curvilinear ILT mask patterns. They are very symmetric. Their quality is very, very nice. This mask pattern written by the multi-beam mask writer has a very good quality. And also, you look at on the right side, you see no matter what kind of curvilinear mask pattern we have, they all print this contact array very nicely, right? They are all rounded contact holes are printed very nicely. And when the pitches changes and the rotation changes, you see the curvilinear mask pattern, they looks very different. But at the end, they all print these very nicely contact holes. All right. Then in the next, I'm going to show you the process window comparison. So what I'm going to show you is a side-by-side comparison between the complex OPC and the TrueMask ILT. Right. So here are the wafer print. They all printed at a different process condition, but the left and the right, they all printed at the exactly same litho condition. So what you can tell here is the quality of those wafer print that done by TrueMask ILT, they always have a really good quality. But you look at the images on the left, they're not that good. Those contact holes are not consistent. The contact holes at the center or at the edge, they all printed differently. And even in some conditions, you see the contacts becomes connected to each other. That's a necking issue. And for some conditions, you see they don't even print at all with OPC. But you look at the wafer print on the right side, done by TrueMask ILT, they all printed with a very high quality, and they are very consistent. Okay, so all of those done are actually the reason we can achieve this, not because of the software, the hardware, but also because this software and hardware are co-designed. So we do use a GPU acceleration, but also we are using a specialized GPU accelerated platform we call CDP, Computational Design Platform, and this is a 6th generation, is specially designed to solve this TrueMask ILT for this product. So together, we can actually process this full chip in 1 day. So in a summary, this TrueMask ILT product is very different from the other conventional ILT product released by other companies. It's the first product that targeted for multi-beam mask writers, so it's a curvilinear ILT, and also because our unique approach using GPU acceleration and also this huge CPU-GPU pair approach, we are able to solve the full chip ILT problem in 1 day. Thank you so much.